Welcome to this new practical activity and the first practical activity actually of part 3 classification. We're super excited. Um, you will see that the case study we will do together is pretty fun. So now we are about to enter a new branch of machine learning where at this time we want to predict a continuous numerical value like in part 2 regression. But this time we will predict a category, a class like for example a binary variable 0 or 1. The classic example is actually two classification to predict a tumor. You know the whether a tumor is and this is actually the case study. We'll do a DNA when how to select the best classification model. And first, we'll do a fun case study with which we will learn how to build each our classification models. So before we start, let's just make sure once again everyone here is on the same page. Um, the link to this for there are containing codes and data sets in 10 parts will be given to you. So connect to that link. You should all be on the same page. We're gonna go into part 3 classification to tackle our first model, logistic regression. So uh, we are now ready to put your well-learned theory into practice. And we're going to put it into practice first with Python. We will implement from scratch and step by step the whole logistic regression implementation. As you can see in this Python 4, though, you have two files first, that logistic regression implementation. Uh, we can open with Google Colab. You have the data set, which is called social network ads. Let's open it and now let's explain the problem. Let's imagine our favorite car company. We will not mention any name here. Uh, let's imagine your favorite car company, uh, that you are a data scientist for that company, and your mission, should you choose to accept it, is to predict which of your previous customers will buy a brand new, beautiful SUV just created by your favorite car company. So your car company has just released this brand new, beautiful, irresistible SUV, and the general manager of this car company has asked you, the most talented data scientist of the company, to predict which customers will buy that new SUV with the highest conversion rate. And to help you, because this general manager has some minimum data science skills and knows and understands that in order to predict this, you need data on which to train your classification model to predict what needs to be predicted, meaning which customers will buy that brand new SUV. That's exactly the data that your general manager gave you. And in this data set, each row corresponds to different customers, and for each of these customers, uh, the features editor, Ben, or for each of these customers, this general manager collected the age and it collected the estimated salary, because when a customer buys a new car with some kind of credit or whatever, it has to provide the estimated salary in the form. So that's how it got the estimated salary. That's your dependent variable, of course. The variable telling whether or not these customers have put previously some older SUV use of this car company. So this company has basically many or makes and models of SUV cars, and all the zeros and the ones that you see here for each customer is in whether or not this customer have bought one of these previews or previous SUV, so that your model will be trained on this data set, and for new customers having a different agent and different estimated salary will predict if yes or no they will buy that new SUV. In this dependent variable, purchase 0 means that the customer didn't buy any previous SUV, and 1 means that the customer bought some previous SUV. And therefore, all the future predictions that will be equal to 1 will probably mean that the customer has a high chance to buy the new SUV if, of course, we offer a great deal. Once we predict the customers that are going to buy the SUV, well, the final step of the strategy will be for the advertising team to post ads of this brand new SUV on social networks, and these ads will be targeted to the customers where we predict that they're going to buy that new SUV. So you see the idea, the predictive model will target your customers, and then the advertising team will use the results of this model to optimize the targeting of future customers. And that is why the name of the data set is called social network ads. So that's the problem. Now we're going to start our logistic regression implementation on your IDE using Google Colab, or if you have Jupyter Notebook, you can use it. So if you follow here, and we will implement this logistic implementation step by step. It is laying out the notebook, and we're about to have it in a second. So that's the whole notebook. It is in a read-only mode. What we have to do is to create a copy of this notebook. We just have to click save a copy in Drive, and this will create a copy, as you can see, of this notebook in which we will be able to re-implement the whole model from scratch. So at the first thing we're going to do is to delete all the code cells, because I want you to take action to learn by doing so. I want you to re-implement all these code cells from scratch. So we're gonna delete all of them. You just have to click them and then click uh, this button, and make sure not to delete the text cells because uh, or text cells, because we want to keep that well highlighted structure. There will be feature scaling for logistic regression. And now we train the logistic regression model, break a new result, and you really have everything in this implementation. You will learn how to predict and ensemble results in the or you how to predict a single result when you deploy your model in production, when you want to predict a single observation, confusion matrix that's to evaluate your model, the visualizations at the end, and once again the data set of only two features. The agent on this can indeed visualize the results on the training or training set and on the test set. Each dimension responds to one feature, and therefore there's many dimensions as there are features. So since we have two features, we'll have a nice to plot, and that's exactly the reason we needed to take two features. The implementations we're about to make works for any data set, the number of features, and we'll prove this to you at the end of this part. When deploying all our classification models on a brand new generic data set with more features, and this is how we will also show you how to select the best model. So, so I would like you to do a little exercise now that you saw the data set and understands it. Since you also have your data pre-processing template, the exercise is I would like you to implement on your own the data pre-processing phase up to the step feature scaling. So we want you to implement on your own this step improving the library or importing the libraries, and this step important the data set, and the steps bringing the or the this into the training set and test set, and finally the last step of the data pre-processing phase, feature scaling. So try it, use the pre-processing template, and in order to implement that step, you need to grab a tool of your data toolkit, and you will find it. You can truly do this on your own. So you did the you did implement now the data pre-processing phase for this logistic regression model. Now we're about to implement the solution together. First, the first natural step was to go to our data pre-processing template to grab all the essential tools which are indeed needed, the first steps of the data pre-processing phase. So let's do this. That's the first thing you were supposed to do. So you copy the cell and then basing it right here in a new code cell for libraries. You paste it. First step done. Import next the data set. Let's go to our data pre-processing template. Um, so you copy this and we'll have to paste. Let's do that. The next step is the splitting the data set into the training set and test set. So that's the first essential steps, which happen most of the time with building a model. Next step is you have to change inside this data pre-processing phase. We have to name the data set. It is not data that CSV, but it is now social network that CSV. So just replace this data set name, social network underscore ads that CSV. So this data pre-processing template was meant for you to not have to change anything. In most situations, you make sure that in your data set you have the features in the first column. These are the two features here and the dependent variable in the last column. And since this automatically selects all the columns except the last one, this selects the last column. And of course, regardless of the number of features you have in your data set, it will automatically select the last column. This will simply select the age and salary in the matrix of features, and the line will simply select the dependent variable in a nice one vector. So you only have to change the name of the data set, social network ad. Next is to upload it in the notebook because in the same uh, lesson, we will actually run these four cells. But before, let's make sure to finish implementing them. So we are connecting to a runtime to enable file browsing. And in second, we should have the upload button. So now we're going to click it to find our whole machine learning, that folder, and we're going to go inside. Then we're gonna go to part 3 classification, then section 14 logistic regression Python, and we're going to select our social network ads that data set. It is exactly the same with, of course, the estimated salary, age, the purchase comes. There you go. So now we're ready to import it. Next step, splitting the data set into the training set and test set. So this will automatically create your training set and test set out of the whole data set. The whole data set composed of the matrix of features X and the dependent variable vector Y. So we do some prints to show you everything because then you know the next step is to apply feature scaling. But again, you could totally leave it like that. So, but I just want to change the slide because since actually we have 400 observations in total, we have 400 customers in this data set. If we choose a test size of 0.25, it will be nice because we will have actually 300 customers in the training set and 100 there in a test. We'll have nice round numbers, so just exceptionally here, recommend a 0.2 as a test set, but all 0.25 is actually totally fine. You will see that we will be able to train our regression model in the future classification models on this dataset with 300 observations and a training set. So 25 is totally fine. We will have a nice training set of 300 and one nice test set of 100 customers. Now we can move on to the next step, feature scaling. Why do we need to apply it? It is actually not required for regression. However, still applying it will improve the training performance and therefore it will also improve the final predictions. You have to understand that for some models, feature scaling is an absolute necessity. However, for other models like regression, it is not a necessity or logistic regression. Still, applying it will improve the training performance and therefore the final prediction. So that's the way we're applying. That's why we're applying it. So now that we got the way, we govern the way, let's proceed to the how are we going to implement feature scaling. There is nothing more simple things to our data pre-processing to get, which we put here. If you haven't, grab it in part 1, data pre-processing. And now in our toolkit, we're going to scroll down to the bottom to find that feature scaling tool, which is actually the last one. That's feature scaling. Let's grab it. And you have to grab the first cell implementing the tool. And now let's go back to our implementation. Let's create a new cell here for feature scaling and let's paste it right inside. And now the last step that you have to do was to figure out what to replace here in this feature scaling. We simply want to feature scale all the features. We want to scale all the features we want to scale, age and salary, and we don't have to scale the dependent variable purchased because its values are 0 and 1 and already in the range of values we want. We're only going to scale these two features, age and estimated salary. What we just had to do as a replacement was just to remove that selection of the indexes here. We selected all indexes down from 3. We don't have to do anything. We can just scale the whole matrix of features. So removing here the index, and we will feature scale our training set and X test. This is absolutely compulsory to do this after splitting the dataset into training set and test in order to avoid information leaked from the test set. That was what you needed to do for data pre-processing. So don't worry about the test size. Now we're gonna do a few prints to see the before and after feature scaling. So right after this code, sales or cells being the data set into the training set, we going to make for prints just to show you. Then first print X train, then print Y train, then print X test, print Y test. After feature scaling, we will just print the sales because we actually don't apply feature scaling to Y and therefore we'll just print first X train again and second X test because this will be the only sets of data that will be changed. So first start by importing the library, import the data set, then split the data set into train set and test set. Next, print X-train and see what it looks like. Scroll down a bit. That's X-trend with first the age and the age feature, and second the column of the estimated salary and the estimated salary feature. We have 300 observations in this training set. We don't have to count them. We have many of them. Now let's print Y train is just to have a look at what we create. This is not compulsory. That's why train with all the purchase decisions on the previous SUV. Zero means that the customer did not buy, and one means yes, the customer bought the previous SUV, and now X test, same, it contains 100 observations correspond to 100 customers for each of them, their age, and their estimated salary. Since X-test is supposed to be some new data in production, we're actually going to suppose that X-test is actually the set of customers who purchased yes or no the new SUV. We're going to pretend that X-test is actually some data when we deploy our model in production so that we can evaluate it on the new observations on the new customers buying. Now y-test. The y-test contains all the purchase decisions of the customers in the test set, meaning whether or not they bought the new EUV. Let's simply apply feature scaling and let's see how X train and X tests are transformed. Play and let's print X train. Now we have some scaled values between -2 and +3. This one is 2.06 minus 1.7. Should be somewhere between -3 and +3. But now we can clearly see that we have both the two features and the same range. The transformer or the age and the transformed salary are now indeed in the same range. And that's exactly what we're supposed to get with feature scaling. Let's scroll down to print X test. And the same, we got the two features, age and salary, taking values in the same range between age and salary, taking values in the same range between somewhere around -3 and +3. This will improve the training performance of the logistic regression model. For the training set, of course, only for the training set. But then when we will deploy our model to predict whether the customers are the test, but yes or no, the new SUV, we will have indeed to apply the predict model on this scaled values. Otherwise, operations will be nonsense. The predict method has to be called a set of features with the same scale as the one that was applied during the training. Now we can move to the next step, about the step where we build and train our logistic regression well on the training set. And we're going to do this with scikit-learn, which therefore leads you to a new exercise. I would like you to figure out on your own how you can build and train that logistic regression model using scikit-learn. And I encourage you to have a look at the API, the whole scikit-learn API to find the class that allows us to build the logistic regression. And then I'm sure that you will know which method to use to train this regression model on the training set. So do it on your own. We will implement a solution together in the next lesson. Let's see if you manage to build and train on your own. This model by, of course, having a look at the cycler and documentation, and more specifically, the scikit-learn API, and by implementing the solution together, this is actually what we will do. We'll right now we'll go to documentation in order to show you how indeed find information on your own, which is here how to build that logistic regression model. Let's open a new tab and search, type scikit. Let's press enter and go to the first link, which is the main page of scikit-learn. Then remember, it's good to go to API here. The other option was to directly type here in the search bar scikit-learn logistic regression class. But again, the API, because indeed to show you, because it contains everything, all the things you can do with scikit. We're going to scroll down to find classification, which is in a module below called linear models. That's because the logistic regression is a linear model, and we will see that in the end with the visualization. How to make the difference between a linear model and a non-linear model. We'll come to that. Before you go, this is where you find in that linear model module of the circuit learn all the linear classifiers. One of them is the logistic regression. So click this and you have the whole documentation of the logistic regression class. This is the name of the class that allows to build the logistic regression model. That's all you needed to get. You could see at exactly the same thing, but by just typing here, the search bar, uh, the cycle uh, logistic regression class. And now what we will only take is the name of the class plus the module. If you want, um, or learn, and then we will rewrite it the right way to import our class and then create the object. So we copy, and then the syntax is to start with from. So from scikit-learn, and then from the linear model module of scikit-learn, and from this linear model module, you import that logistic regression class. That's the usual syntax we take from the linear model module of the scikit-learning library. We will now create the logistic regression class. And now the next step is to create an object of this logistic regression class, which will be exactly the logistic regression model itself. No longer in regression, we're going to call our other classification models of this part 3. So classifier, the next step, we have to call the class. That's how we create an instance of a class. And then we add some parentheses. And now the question is, do we have to input any parameters? Well, we would just like to build the model, but then don't worry. Uh, this will come later. Just focus on how to build and train the simple logistic regression model, which will yet provide amazing results. So no parameters here. We'll just enter this random state parameter, which will allow us to get the same results displayed on our notebooks. This is just for teaching purposes. You don't have to do it on your own data sets for your own problems. So random state, and we'll set that equal to 0. Final step, we have to take first RA classifier, and then what we want to do is to train our classifier on the training set, because remember that this line of code only builds the logistic regression model but doesn't train it yet. And this next line is indeed the final step where we train our classifier on the training set. Remember to do this, we have to call the fit method, which takes as input two entities, two sets of data. The first one is the matrix of features of the training set, and the second one is the dependent variable vector of the training set. All the purchase decisions of the dependent variable vector correspond to the same customers of the features or of the matrix of features. We had to input here was simply X train for the matrix of features of the training set, and then Y train for the dependent variable vector of the same training set. There you go, you obtain this, and also if you tried, that's how you build the logistic regression model. That's one extra model we have. We're going to have many more. We will train on how to select the best one for any data set. So let's run this cell. This will indeed build and train the logistic regression model and Y train. By the way, you see all the parameters of the logistic regression. You can tune the most famous one to see, which is the inverse of the regularization strength, meaning that the smaller is C, the stronger will be the regularization, and therefore the more it will protect you from overfitting. That here will just give the default value of 1. ready to move into the next step, predicting a new result. So now, new exercise for you because we already did it with regression. Um, so now, new exercise for you because we already did it with regression before, uh, or you take your regressor and then call the predict model to predict the result of a single observation. And so here, the exercise that I would like you to do is to predict the purchase decision of a single result, the purchase decision of a single customer, and which one would like to predict. The purchase decision of the first customer in the test set who you will see in 30 years old and earns an estimated salary of $87,000. So I would like you to take these two inputs, these two features with these values, 30 years old and $87,000 at the estimated salary, and now would like you to predict whether this customer has yes or no, the SUV. You have the answer is white says, you take the first result of white test and thus you'll be able to compare your prediction to the real result to figure out whether your prediction was correct. So there you are. Do the exercise. Try to do this on your own first. So I hope you did amazing with the new exercise, which was to predict the purchase decision of a new customer in a test set. That was the first customer who is actually 30 years old and earns an estimated salary of $87,000. If we have a look at our test set, the original tested before this uh, scaling, this is exactly the customer you had to input in your method in order to predict the purchase decision. And now in this to Q, we're going to check two things. That first, you got the right implementation and the predict method, and mostly the right input inside the predict method. And secondly, we will also check if the prediction is correct. We're going to have a look at why test. The purchase decision of that first customer is exactly this one because white test contains all the real results here, all the real purchase decision. So we're going to see if indeed our model was able to make a correct prediction by predicting zero for this first customer of age 30, salary 87,000. Let's proceed to the solution. Here it is predicting a new result. We will leave the training. Let's create a new code. And now what was the first step? The first step was to take our classifier because of course the predict method, as any other method, has to be called from the classify object itself. So we take our classify object and then from this object we're going to call this predict method. By the way, let me show you this again. You have other predict method which are predict low probability, which will return the logarithmic function of the probability that your prediction is 1, that the purchase decision is 1. You also have to predict uh, prob method, which returns directly the probability that the purchase decision is 1. So depending on whether you want to have directly the final prediction 0 or 1, or the probability that the dependent variable is equal to 1, you had the choice between predict and predict prob, probber. So here we're going to predict because we directly want to get the prediction whether or not the first customer of the test set per se, yes or no, the SUV. We're going to add some parentheses. Um, what did you put inside the predict method in order to predict the purchase decision of that customer who is 30 years old and earns a salary of $87,000? Well, first of all, let's remind the essential. Any single observation inside the predict method has to be input in a double pair of square brackets. Why is that? That's because the predict method expect from its input a two-dimensional array. And how do we create a two-dimensional array with only one observation, meaning only one row? Because what true about input is a two-dimensional matrix of one row and two columns where the row corresponds to that single customer, and the columns correspond in fact to the features that age in the first column and salary in the second column. Um, so this second pair of square brackets, which good response to columns, you have to input two values of these two features to age and the salary. And therefore, since our first customer is 30 years old and have a salary of $87,000, two features here that we had input in this, therefore two comes here is first 30 and then $87,000. The first thing you must absolutely do, you must have the right reflex. Input your single observation within a double pair of square brackets to give the expected format of the two-dimensional array to your prediction method, or to your predict method. You had to do something else, which is to scale that single observation, because 30 years all here and $87,000 as the estimated salary are in the original scale. Before applying feature scaling standardization, since our model was actually trained, as we can see on X train and Y train, which were just previously feature scaled, that's the result of feature scaling. Um, to predict, methods can only be applied to observations where the features have the exact same scale as the one that was used for the training. And therefore, here we need to apply the transport method in order to give us, which has to take as input this whole single predict input into the array. All right? And the second one, that's the solution to our previous exercise. Congratulations if you got this right, because you had to pay attention to two things. First, the right format added to the array here for your input, and then transforming that input, those features, to get the right scale for your predict method. Now we're actually ready to run this, but we'll actually get the better output. Nice of one, if we put all this into a print that output of the print method. So let's press play. And remember, let's see if our classifier manages to predict the right outcome, meaning the right um, purchase decision, which according to the test set, which contains the real result, is zero, meaning that first customer of age 30 with salary $87,000 doesn't buy that new SUV. So let's press play and let's see if it is zero. And great, it is zero. For now it's zero. The model did amazing here on this single observation or customer. We're going to move on to the next step, which will be to predict the test results so that we'll surely know exactly how to do it. Make sure to figure out if you need to apply feature scaling or not, and you will get to the right solution. Please display the vector of predictions, the vector of predicted values, the purchase decisions for the test set, and the vector of the real purchase decisions of the same test next to each other. And you don't have to figure out how to implement that again. I want you to be efficient, encourage you to take that little piece of code we made in many of the models to display this efficiently. So let's see if you got this right again, predicting the test results and displaying the vector of the predictions next to the vector of the real results, meaning the real purchase decisions. And we want you to juggle with all your toolkits, whether it is the data pre-processing toolkit or your other machine learning models where you have indeed several tools inside, because now the tool we would like to use is that in a little piece of code that allows to display the two vectors of predicted results and real results. So to be the most efficient as you can was to go to part 2, regression, and then into the multiple linear regression folder, and then open this multiple linear regression implementation, which indeed contains inside. So open it, that tool allowing to display two vectors of predictive results and real results. So we implemented it many times. That's why want to do it again here in our logistic regression implementation and incentivize you to be the most efficient as you can by juggling between your different models implementations. Also, if you did this, if you had the reflex to grab that tool right here in multiple linear regression or many other models where we implemented that, you did amazing. So here we're gonna take this and you're implemented, re-implement to yourself. That's also amazing if you manage to be more efficient than how we were about to be. What we only have to do here is to copy this little piece of code, that tool, and pasted in a new code cell here to predict the test set results because we have all the same names here for the vector of predictions, which will be the result of the predicted method applied to test set and called, of course, from our not regressive object, but classifier object. Thus, that's the first change you had to make. And then, since this time, our predicted purchase decisions and the real purchase decisions are either 0 or 1, you don't need to add anything here. Force a number of decimals after the comma to be only 2. Here we can only deal with integers, so we can remove this. And then final question, do you have to change anything? Absolutely not. And that's what I mean by grabbing a tool and applying it on your new model. The only thing to change, uh, the name of the model type from regressor to classifier. Let's check it out. Let's press play and we get two vectors next to each other with first on the left. Your vector of predictions of predicted purchase decisions for all the customers. Of course, the test set. This was applied to X test here, so that's all the customers of the test set. And on the right, in the second column, you have the real purchase decisions. And so here, what is interesting is to compare the predicted purchase decisions to the real ones for all the customers in the test. Let's see for the first customer of the test set. Remember of age 30 and salary $87,000. The prediction is no. This customer didn't buy the new SUV and the real result is no. In reality, that customer didn't buy the new SUV. Same for the second customer, was predicted not to buy and it did not buy that new SUV. Third customer actually bought and our model predicted that indeed this new customer bought it. Well, it's funny, we actually have a lot of correct predictions, and this is so far is correct. We have our first incorrect prediction here. Our logistic regression model predicted that this particular customer didn't buy because we have a prediction of 0 here. But in reality, that customer bought that new amazing SUV. Because the real result here is 1, then here it is correct. Another incorrect prediction where our model predicted again that this didn't buy the SUV, whereas in reality, that customer bought the new SUV. And you see, so that looks really good. We'll get a very nice confusion matrix. What it is, and mostly a very good accuracy because accuracy is in the test, and of course, is simply the number of correct predictions divided by the total number of observations in the test. And this is exactly what we're about to get into to test, to set. We will not only get the confusion matrix showing, so the confusion matrix will show us exactly the number of correct predictions and the number of incorrect predictions for the two cases where the real result was 0 or 1. We'll have a nice matrix showing how many mistakes and correct predictions our model made. Inside the same new step or code cell, we will compute the accuracy. We'll see what is the percentage of correct predictions our model made on the test. Should So you should try it again because once again, you just have to go to the API of the scikit-learn and figure out how to make that confusion matrix and how to compute the accuracy. So we'll have to look into the matrix module from scikit-learn, and then you can really find the tools you need with that. Now we have 3 steps left, and the one we're about to implement is the confusion matrix, which is a simple 2D matrix, 2 rows, 2 columns, which will show us the numbers of correct predictions we did in both cases in operating 0 or 1. How many incorrect predictions we did in same both cases 0 or 1. So that will be a nice way to see quickly where did we did right and wrong. Also that we will compute the accuracy. At the end of the previous uh, this, we will ask you to try to figure it out on your own by looking at the scikit-learn API. So going to show you how to navigate it, and first the information we want, the tool that we need. Let's go back to the welcome page of scikit-learn. Then you have to go to API here, which contains all the classes and functions from the different modules, and look into the module called metrics. So we just have to scroll down a bit and we will find very soon metrics. It's in the alphabetical order. So there it is, matrix, and then it's very well organized. You have the regression matrix, in which we already covered the most important ones, and the classification matrix. And here we are dealing with classification. You have to look into here, and now we're getting closer. We're getting, uh, or what we do we see inside? We see matrix, confusion matrix, and that's exactly what we'll take in order to build this confusion matrix. And then what we do is simply have a look at one of the examples, because it usually contains the code on how to build such a tool. The matrix, but it usually give you this example on some random values of dependent variables. It also tells you how to apply this confusion matrix onto the vector of real results and effective or real results and predicted predictions. Confusion matrix function into the vectors of prediction and real results. You see what I'm trying to do here? Don't do this. We do this in order to train you to be independent whenever you need a new information or a new tool that you need, and training you on how to find it in the scikit-learn API. The same, working with TensorFlow, um, this is very important. So inside this confusion matrix function, what do we have to replace? The vector here of real results y true, since we actually want to distinguish the vector of real results in the training set and test set, called ry true vectors. So say y train for the training set and y test for the test set. Since of course the confusion matrix is actually usually evaluated on the test set, for new observations here we have to replace y true by y test, so that we will get indeed the confusion matrix showing the correct predictions and the incorrect predictions for both cases 0 and on the test set. We'll actually output of this confusion matrix function of play to whites, and so we will actually put the output of this confusion matrix function applied to y-test and y-pred into a new variable, which we're going to call CM, which stands for confusion matrix, and which will be exactly the output returned by this confusion matrix function. And we'll add the final print C, and in order to print indeed that confusion matrix, these are the 3 lines of code that allow indeed to build that confusion matrix and print it. And now remember that also asked you to compute the accuracy, and to do this we just had to do exactly the same as which we just did. To find that information, try to press pause on the video and find it yourself. If not already, we're gonna go back to that matrix module. remember the metrics module from the second in the in library, and we're going to look back into this metrics section to find the accuracy. According to, or this is actually the first one, accuracy score, which computed the accuracy classification score, the rate of correct predictions. Let's click this link and we will get indeed all the documentation on this accuracy score function, which returns the accuracy of your model on whatever set of data and will apply, of course, to the test set. So first of all, as we can see, this accuracy score function belongs to the same metrics module. And we don't have to take all of this again. We can just take that name of the function here and we'll show you what to do just next to confusion matrix. You just add a comma and then you can paste this other function. You need to know which you have to import still from that matrix module from the scikit-learn library. Now we have it and now we can use it. Just below, we will actually call it. In order to do this efficiently, we can just take the example here and right below we paste and we just replace once again y true by y test so that we can get indeed the accuracy under test set. And here we don't have to do a print because this accuracy score will directly return that accuracy or that rate of correct prediction. So there you go. You can just play this, run the cell, and you have that. You have here the confusion matrix showing that we have indeed 65 correct predictions of the class 0, meaning the customers of the test set who didn't buy the new SUV, then 24 correct predictions of the class 1, meaning correct predictions of the customers who bought the SUV, and then 3 incorrect predictions of the class 1, meaning 3 incorrect predictions of the customers who, but in reality, that SUV, but were predicted not to, and 8 incorrect predictions of the class 0, meaning 8 customers who in reality didn't buy the SUV, but were predicted to buy it. So you see the confusion matrix has, or it's very easy to read, and we can indeed get the main information of our predictions. And finally, that little number that we have here is, of course, the accuracy. And we got all points 89, which means that we had 89% of correct predictions in the test set. And there are 100 observations in the test, which means that we had indeed 89 correct predictions. 65 year plus 24 is equal indeed to 89. But for any size of a test set, this would mean that you had 89% of correct predictions. That's exactly the accuracy. It is the rate of correct predictions. Now you quickly evaluate a classification model. The accuracy is usually the right metric to use when evaluating your classification models. You have it in the toolkit. So here we go for our final step. And we're going to visualize not only the training set results, but also the test results. And this will be super interesting because we will actually see how the logistic regression classifier was actually trained to classify our customer as our observations into two different classes, 0 or 1. We have super nice results showing all the real results in both the training set, in a test set, and also the prediction results. The regions where our predictions are 0 and the other region where the predictions are 1. So here we are at the final step of this implementation, the most exciting one, because this is the step where we're going to visualize on a nice 2D plot the prediction curve and the prediction regions of the logistic regression model. So more specifically, what we're about to plot is a two-dimensional pie plot with therefore two axes, x and y on the x-axis. We have the first feature corresponding to age, and on the y-axis you'll have the estimated salary. Each of the points, the observation points you will see on the plot will correspond to a specific customer. It will either be a customer of the training set on the plot of the training set results, or a customer of the test set on the plot of the test results. And what is most interesting to see in this plot will be the prediction regions, meaning the regions where our logistic regression will predict the class 0, meaning the customers didn't buy the SUV, and the other region where our regression model predicts the class 1, meaning the customer uh, buy the SUV. And lastly, what will be really interesting is the curve separating these two regions, the region of the prediction 0 and the region of prediction 1. And this is exactly how we're going to see the difference between linear classifiers and nonlinear classifiers. We are starting with one classification model, but we will see in the next section of this part that the prediction boundary, we call this the prediction boundary between these two prediction regions will be different depending on whether or not your classifier is linear. So let's start first by visualizing this training set and test results for the model. So the code to visualize this is pretty advanced, and not only it is advanced, but also you will never use it again in your career, or let's say you will never have to implement that again. Why? Because you will mostly work with data sets having many features, more than two. And here, the only reason why we have a data set of two features is so that we can be able to visualize and this prediction regions and prediction boundary, because in order to visualize this we need maximum two features because one feature corresponds to one dimension in this plot. So there's a code to visualize. This result is only useful for training purposes, and it will not be useful for your future uh, models. So we suggest that we don't waste too much time understanding the whole code and re-implement ourselves, because we're gonna show you to the right way, the original implementation. So you will see that the code is advanced. It's not like plotting a regression curve like we did in part 2. So that's the test result. We show you the trains that result. Um, it uses a lot of tricks to plot all the observation points. If you want to have to look at it and understand it, it's fine. But really, for others, it's totally okay if we don't cover this code in detail, just so that we can show you the difference. We're using this so that we can show you. So how it's done, basically, what we do is we create a grid, this frame here containing all the ages of your feature and all the salaries, the ranges, and you create this grid with a high density, meaning that the pixels of this grid are not separated one by one, but every all points. For example, age, it goes from 10 to 10.25 to 10.5 to 10.75 to 11 up to 69, 69.25. So up to somewhere around 149,000 So resulting in having super dense points inside the grid. And then the trick, what we did is not only we plotted all the real observation points in the grid, so all the points that you see here are the tumors of either your training set, and then later on your test set, the green points are of course the customers who bought the SUV represented by 1 year, and the red points are of course the customers who didn't buy the SUV represented by 0 here. All the points are your observation points. So to plot the prediction regions, That prediction boundary here separating the two regions is to apply to the predict method onto each of these dense points in the grid, so that all the dense points here in this region were actually predicted to be zero, meaning all the other customers inside this region are predicted not to buy SUV, and all the observations points in the green region are actually predicted to buy SUV, because the region here is green, representing the predictions of one, and all the red points here, red region, are old observation points predicted as zero, meaning all the customers who were predicted not to buy the SUV. So how that is how it works. Then you don't have to understand all the techniques used to implement this. Once again, you will probably never have to implement that kind of code. You So what we're going to do now is we're going to get that whole code from the original, and we're going to paste it inside our new implementation. And we're going to do the same for the test set. Then we'll actually try not to show you the test now, but let's get the code. Let's paste that below in a new code cell. And now let's enjoy the results. So what we're gonna do is first execute this cell. It's gonna take a little while because the step is 0.25, meaning we will get a very dense grid as I've just explained. The predict method is applied on each of these dense points of the grid, and that's why there are actually a lot of predictions to compute. That's why it's taking a little time. But there you go, it's coming. We just got the results of the training set. Let's also plot now the results of the test set. So we can just let it run and start by observing and interpreting the results of the training set. So just to recap, you have to understand four things in this plot is that all the points that you see, whether they're red or green, are the real customers and the real results in the training set. The green points correspond, of course, to the customers who put the or buy the who put the points correspond to the customers who put who bought the SUVs, and the red correspond to the customers who didn't buy any SUV. And then the other two things to understand is that those colored regions, the red and the green, are the prediction regions. So this region is the region where our model predicts the customer didn't buy the SUV, and this region uh, predicts that the customers bought the SUV. And so, in order to figure out where to correct predictions are and incorrect predictions are, the correct predictions are where we have some observation points with the same color as the green region, and the incorrect predictions are where we have some observation points with a color that is different than the prediction regions. For example, this customer here who in reality bought the SUV corresponding to one here is actually an incorrect prediction because it falls into the wrong region, the red region, and vice versa. Here in reality didn't buy the SUV because it corresponds to zero, was a wrong prediction because it falls into the green region where customers are predicted to buy the SUV. Then finally, what's the most interesting? This is the prediction boundary. As you understood, the prediction boundary is between those two prediction regions. The green prediction region and the red prediction region, it is where your classifiers separate. Basically, the two classes, the class 1 and the class 2. And now you have to understand something very important. It is the fact that the observation that the prediction curve of the logistic regression model actually is actually a straight line for one specific reason, because the logistics regression model is a linear classifier. For any linear classifier, the prediction boundary or the prediction curve will always be a straight line. in 2 dimensions, in 3 dimensions, it will be a straight line. So that's what we get for linear classifiers. And what we will be really interesting to see in the next section when building our classification models is that for the nonlinear models like naive Bayes or SVM with nonlinear kernel, you will see that the prediction curve or the prediction boundary will actually not be a straight line. So uh, remember that this R was trained, and therefore that's kind of easy to provide such results because these are exactly the observations of the training. But now what we would like to observations of the test set are new customers which our model wasn't trained. And so we have to see if our model was still able to separate the two classes, meaning the customers who bought the SUV and the customers who didn't buy the SUV, even despite the fact that these are new customers on which the model wasn't trained. And that's exactly what we're about to see now when visualizing test results. We already executed the sales here, and so these are the test results, and still our logistic regression model was perfectly able to separate the two classes zero, all those red points here, and one, all those green points that are still some. There are still incorrect predictions. Like this, who didn't buy the new brand new SUV but predicted to buy it, and a few incorrect predictions of the other class, meaning these customers who in reality bought the SUV but were predicted not to because they fell in the red in the red, not the green region. And a few incorrect predictions here of the other class, meaning these customers who in reality bought the SUV but were predicted not to because they fell in the red region. And so, how can we conclude here? What should we conclude, and what are the takeaways and we should get for our future classification models? Well, the first, the model does a very good job at separating our two classes and therefore at predicting whether the customers bought SUV. But we actually would hope to build a model that has less prediction errors. And how can we build prediction boundary that is something else than a straight line? Because even if you try to take a prediction line, for example, ultimately some kind of curve, some kind of prediction curve that goes this way, catches all the red points in all the red customers, and then go around like this in order to catch all the red points, the red customers, and leave all the green customers inside the green region. You might guess this is what we might be able to get with non-linear classifiers. Be ready for some even more important classification models that manage to separate even better these two classes. So that was the teaser for the next section. Now we hope you enjoy this implementation of the logistic regression model. The implementation we did here for the logistic regression model will work for all our other classification models. And by that, we mean that the implementation we did here is actually a very good code template. It is a code template for classification because in order to implement the other classification models, we will only have to change one single cell of the implementation, which is the cell where we build and train the classification model. We will only have to change this cell where we build a classifier and train it on the training set, and all the rest will be the same. We won't have to change anything here because we will just call our classifier to predict this single result and then all the results in a test set. And same for the visualization. We won't have to change anything except the name of the model here because indeed all the variable names will be the same. The classifier, which here is the logistic regression model. But in the next section, we will be the other classification model. We have the same variable names for the training set and test set. That's why we won't have anything to change in our future implementations and the classification models except the part where we build and train our classification model. So we will be extremely efficient in our future implementations of the models because we will only have to recode that cell here and it will just re-implement this to implement the right classification model, and then we will do a run all to enjoy at the end the final results. The new prediction regions, and especially the ones for the nonlinear models, where we are hoping to get a regression curve that goes like this in order to get the maximum right predictions